All right, so continuing where we were more or less, but kind of jump back and talk more about, so most of the things I did last time we talked, I specialized to the case. So we're still in Introduction to A Calculus, right?
Mm-hmm.
Which of course is posted on the archive under title the pretty much same, I think. And so especially last time, I assumed that A was basically, for the most part, equal to Rn, right?
Yeah.
And so I assumed A was equal to Rn as a point set, and for the most part, I used the basis, which was formed by, E1, E2, the standard basis, right? Where, in addition, we assumed that E1 was the identity, the number 1 in the algebra, right? And that's a special, I did show an example or two where that wasn't the case. Like we looked at the direct product algebra, where the identity was 1 comma 1. But many of the most beautiful theorems are subject to this particular convention. This particular convention aligns most closely with what we typically see in complex analysis and other places where this kind of like extended calculus is done. However, it's good to, I think, develop a theory which doesn't assume this, right? And I'd like to just, make some definitions. What about general basis, all right? For the algebra A, all right? And A is not necessarily equal to Rn, okay? It could be, right? But I'm just saying, think more abstractly. Maybe the algebra is a set of matrices or particular type of functions, whatever. And all right. Given the interjections of my son, I think I'm gonna put the mic back about 10%, so we don't have random Isaac. Oh. I think it'll still pick me up if I go to the 65 setting. There we go. All right, so here's the big picture. We've got our algebra, right?
Yep. And
we also have the matrices, which represent the algebra, all right? And we also have the right linear maps on the algebra. And the right linear maps on the algebra I've denoted by, I believe, R sub A.
Right linear algebras?
Yeah, R sub, let's see here, definition 4.3, R sub A defines the set of all right A linear transformations. So, no. So R sub A, so that makes T a mapping from A to A, such that T of X star Y is equal to T of X star Y. If we're assuming that star is algebraic multiplication star, okay?
I think you defined it here as right A linear maps have these. Well, yeah, because left multiplication by an alpha is right A linear, right?
Mm-hmm.
And you define it as a cursive L sub alpha.
Oh yeah, that's a particular thing in here. But good point. So if alpha is an element up here, alpha is a particular number, then down here L sub alpha is a particular mapping
Okay.
for that example alpha. And then, so in fact, that is a, you could make that correspondence, alpha maps to R alpha. Now, then the matrix, well, the matrices corresponding to the algebra. And you see this right here, the left multiplication by alpha, there really is no, I can define the mapping. Let's see here, phi of alpha equal to L sub alpha, right? And I can define that map, all right? And it's definitely a linear map of vector spaces. You can prove that A and R sub A are vector spaces. It's by assumption A is a vector space, okay, that's part of our definition of algebra, but anyway, this is a linear map from A to R sub A because we proved that L sub alpha is a right linear map. My larger point here for our current discussion is that has no dependence on basis whatsoever.
No.
All right. While on the other hand, what's the matrix of alpha? Like, how do you define the matrix of alpha? Well, there, almost necessarily, you're going to have to make a choice of basis. The reason we didn't have to do that last time is because we were using the standard basis, and the case that this was equal to Rn. So in that case, there's a natural choice for the basis. You just use the standard basis for your basis of the algebra.
I thought we used the basis that we separated to everything is multiplicative or E1 or E2, depending on which one we chose.
Yes, but that's the standard basis. E1, E2, En, that's the standard basis.
Okay.
So we were using the standard basis and subject to a special assumption about the algebra that the algebra is written such that the first element of the standard basis is the unity in the algebra. But if we don't have all that special trappings, then how do you define the matrix, right?
Yeah.
So, so that's the question, right? And the way to do it, or at least one way to do it, have a mapping from here to here, would be to kind of go through down here, essentially. So we'll say that, I'm trying to stick with the notation of my paper here. Did I make a notation?
Where are you at?
On page 9 and 10.
Okay, that's what I found.
So yeah, I'm defining, this is the big M. Big M. All right. And so what's big M of alpha over here, right? What is that? Okay.
Yeah.
How do I define a map from there? So first of all, I haven't really explained what this is yet. First of all, that's not quite complete. For an abstract algebra, and by that I'm not necessarily talking about abstract algebra, obviously, right?
Yeah.
This is beyond abstract algebra, your course, because you're talking about rings and such. But I put a beta here because it's really there's a basis dependence for the representation of the algebra.
Yeah, that's what I was thinking. I was like, how can you?
You have to, yeah. But past that, all this is going to be is it's the set of matrices of let's say T with respect to the beta basis, such that T is an element of the is right linear, right? So this is of course a subspace of n by n matrices for us. And so getting to the point here, the way to define this map, the representation map for alpha, what we're going to do is we're just going to take the beta matrix of the left regular, so like L sub alpha, right? So which alpha? Well, I mean, I think it's just alpha. It's just this, L alpha. And then that's what the map is. Yeah, this is my equation 16. And this is my definition for the big M.
Yeah, but it still looks like the standard basis.
Which one?
Looking at your equation 16, B1 out to Bn.
Oh, yes. But notice that there are coordinate vectors now, right? Like,
Yeah.
so it's with respect to the beta basis there, and like that was not present in our last discussion. Like we just put all we did was like alpha times E1, alpha
Yeah.
times E, So with this map M, at the moment I've called this map phi. I don't know what I called it in the notes. I almost don't want to worry about it. Let's see here. Maybe I should come up with new names so I don't accidentally redefine something in the notes with a different letter. I called it psi. I called this psi.
Yeah, you did. That's right.
All right. Really M is the composition of psi and the. I don't have a notation for this except that it's take the matrix of the map with respect to the beta basis map. I mean, I never thought about this before, but taking the matrix of a map is itself a linear mapping from the set of linear transformations to the set of matrices, and it's an isomorphism. Basically, I'll use F for a second. F is a mapping from, say, linear transformations from V to W. I'm working in real context, so let's say Rm by n. And so these things. I'm getting too far off topic here, but anyway, you can come up with a basis for these things and just basically map that basis over here to the Eij basis in a one-to-one way, and that linearly extended gives you the isomorphism. But here, I'm just talking about f of t is equal to t beta gamma. So here I'm assuming, basis beta on V and gamma on W, I suppose. But all right, enough about that. So the larger point here that I was trying to get to, before I distracted myself, my bad, is that these maps, this matrix, the representation map that takes the algebra element over to here to this matrix, or this psi map which takes the algebra element down here to the left multiplication map, these are in fact isomorphisms of algebras. All right, and so let's see if we can maybe just talk about how to understand that for a second here. So let's see here. Well, I mean, this is a nice formula in principle, but like, let's see here. So if we have, I'll try to focus on the most sort of exciting part of it. The linearity part is not that interesting. The product part is kind of what's more interesting. So if we have m alpha beta, right, then that is by definition the matrix of the alpha times beta left linear map, right? Ooh, bad choice. Poor choice.
Say gamma.
why I started using alpha as element of the algebra. I'm not sure. There must have been a reason, but anyway. So my obnoxious. A lot of other people just put 1 beta because it's just understood. But I put beta beta so that when I want to talk about beta gamma, it's the same notation. Whatever. Anyway, so we proved last time that this is L alpha composed of L gamma. Because of how left multiplication works and the associativity, and then this is like linear algebra. The matrix of composition is the matrix multiplication of the composed maps. The number of my betas is multiplied.
So if it's left linear, wouldn't the function only hit the alpha component?
Let's see here. So we had L alpha times gamma of x, right?
Mm-hmm.
That's alpha times gamma times x, right?
Mm-hmm.
Which is alpha times gamma times x, which is
we have associativity.
L alpha of gamma times x, right? Which is L alpha of L gamma of x. And since that holds for all x, we have that. So that's how I can go from here to here. And then this is just like linear algebra. The matrix of a composite is the product of the matrices composed. But that is to say, this is M alpha times M beta. Oh, gamma rather, my bad. And you know, I was almost slightly more obnoxious because really this M map as I've currently defined it, maybe it should be like, and I might adorn this with an M upper beta or something to be more honest, because this is the representation map with respect to the basis beta. So I mean, if I wanted to be more explicit about the basis dependent, I might adorn all of these M's, big M's, with a beta. All right. Now, the itch I'm trying to scratch here, like the deeper question is, we have an algebra, we make a choice of basis, right? So, like, what does that do to us? Like, what if we made a different choice of basis? How is that going to affect the objects we're studying? Right? Like,
yeah, I mean, it depends. I mean, you would it could affect it. We're talking about a ring, or are we talking about any abstract algebra?
just the associative algebra that we study here.
It could affect multiplication in certain ways, depending on what you classify the
Yeah,
basis as.
I think it would definitely give us like a different subalgebra of Rn by n. The question is, how are those two different subalgebras like related? So at the risk of getting into trouble here, I'm going to erase my RA and say, okay, so suppose that I have a different choice of basis, say can I erase the, this over here?
One second. I'm just writing the
I'll be right back. if we chose a different map, you know, and I'll call this, I'm going to call it gamma now. All right. So suppose gamma is another, you know, basis for the algebra. So we can look at, you know, MA with respect to gamma. And so of course, there we would define I'd say m gamma of alpha would be equal to the matrix of the left multiplication by alpha map with respect to the gamma basis. One moment, let me close the door to the piano. Every day, I have to send children to tell them, close the door to the room with the piano when you're practicing, please. It's so loud. All right. So in contrast over here, this is the M upper beta map, right? And so how are these related? Now that's just a question of linear algebra. How is that?
well, they should be. They're essentially the same thing mapping wise. We're just using different bases.
Right. So how does the matrix of a given linear map compare if you use two different choices of basis? Is the question, right?
Oh well, yeah. Well, what you're building the basis from is still that original algebra.
Yeah, I'm trying to. I don't know. You'll forgive me a brief detour into linear algebra again here for a second. We've got T, right?
Mm-hmm.
And we're going from basically A to A, right? And so we've got this coordinate map with respect to the basis, coordinate map with respect to the basis, right? And down here, we've got Rn, and here we have, you know, multiplication of the map, T, beta, beta, right? And left multiplication by T, by this map, is defined to be, basically we go this way, right? So we finish with phi beta, T goes in the middle, and we start with phi beta inverse. And
So when you're saying A, is that any, or that has to be the same algebra?
same algebra. I'm just talking about the matrix of the mapping on the algebra, a linear map on the algebra with respect to choice of basis. Like this is how we define the matrix of such a map in terms of composition of like coordinate maps and the inverse coordinate map and such. But now,
Well, can you break that down more? Is with associativity just to get you T?
well, we're trying to describe this though as it relates to the choice of basis, you know.
Mm-hmm.
In contrast, if we had done with respect to the gamma basis, we would have had, instead of betas, we would have had gammas, right? So the question is, how is this and that related, right? And let's see here. I can change one of these to the other by just some kind of sneaky mapping stuff here. So like, how can I change a gamma to a beta? How about this? If I change this to phi gamma composed with phi beta inverse composed with phi beta. See that? So what I'm doing is so what I'm doing at the moment is I'm showing you how to derive coordinate change for linear maps using composition of maps. This right here is all of that. I just shoved in a copy of the identity. This is the identity map. And now there's still the t's in the middle, right? And on the flip side, over here, I'm going to put in another copy of the identity map, but in the opposite sense. I'm going to start with phi beta inverse, I'm going to compose it with phi beta, and I've still got the phi gamma inverse all the way down, right on up here. Now this is just straight up an identity.
So why do you have to plug in both identities? Why can't you just plug in the one and then once it maps to t?
Right. Well, what I'm trying to derive at the moment is the relation of the matrix of the map with respect to one basis versus another.
Okay.
And so I'm looking for a formula which involves both. And so like I've got the gamma gamma matrix, right? I'm trying to work my way over to the beta beta matrix. To get that, I need this composition of maps, right? But at the level of map composition, all I can really do is just insert copies of the identity map. Or at least that's one thing I can do. And so that's what I've done here. And the reason I've done that is because now, see this right here, is this.
Oh, so you can squeeze that in now.
Right, so what I have is the composition of, let me call this map altogether left multiplication by p, composed with left multiplication by t beta beta, composed with, now I said left multiplication by p, and so if I use the notation left multiplication by p, what I'm saying is that this mapping, I'm claiming that there exists a matrix P such that LP, which is phi gamma composed with phi beta inverse, right? Now this notation, L sub P for me, is the notation left matrix multiplication by the matrix P. Is that a fair claim? See, phi beta inverse is a mapping from Rn up to A. Phi gamma is a mapping from A back to Rn. All right? And both, these are the coordinate maps. The gamma coordinate map and the inverse beta coordinate map. These are both linear maps. The composition of linear maps is linear. Therefore, L sub P is linear. It being linear, there exists a matrix, let's call it P. All right. I mean, here's a formula for P. P is equal to the standard matrix of phi gamma composed with phi beta inverse for what it's worth.
So would you put LP and then
yeah, what's this?
LT?
What's that?
Would that be LP inverse?
It would be LP inverse because that is in fact this is the
sock shoes.
Sock shoes. That's the LP inverse, right? And also we know P inverse exists because well, it's the composition of coordinate maps, and those are invertible maps. All right. At this point, check out what we have. We have that the left multiplication by that matrix is equal to the composition of these left multiplications. But by linear algebra, early matrix theory, this is left multiplication by the product P, T, beta, beta, P inverse. Because if we have
Oh, they're all yeah.
They're
all
matrix left multiplication by the matrix.
Mhm.
And so, but you know, the mapping, the L mapping, if you will, is itself an isomorphism. So the fact that this is equal to that implies that the matrices are equal. Therefore, well, here you go. This is the mystery to solve. The matrix of T with respect to the gamma basis is equal to P matrix of T with respect to the beta basis, P inverse.
So that would not be, and this would be. Okay. And then. P.
I'm going to zoom in a bit. This might be too fuzzy.
T.
There we go. So, what I've shown you is that if we want to understand the relation between two different regular representations of the algebra, one with respect to the basis beta, the other with respect to the basis gamma, the relation of these subalgebras, it's very, very simple.
Yeah, it's the same thing we've been doing.
Right, and you notice they're related by conjugation. This is conjugation. The matrix P, it's fixed by the choices of, it's got nothing to do with the element, it has nothing to do with T, it just has to do with your choices of basis, beta, and gamma. So, these two things, these are related by conjugation. You can say they're conjugate subalgebras, like the set of n-byte matrices. Now, it doesn't mean that they're the same. They could look quite different as matrices, but many properties that they have will be shared. Now, so the big theorem here, of course, so I'm actually sort of getting into the weeds a little bit here, but the big theorem is just this theorem. The algebra is isomorphic to the right linear maps on the algebra, and that's isomorphic to the matrix representation of the algebra with respect to any choice of basis beta. And I've described for you the explicit, isomorphisms. The isomorphism to go from here to here is just assignment of left multiplication map.
Yeah.
To go from here to here, we can take the matrix of the left multiplication map, and you can define inverses as well. Although the inverses get kind of tricky, unless your basis has like a really special structure, right? Like these formulas become more simple if beta. Well, let me just write it down. If beta is equal to what? If beta is equal to V1, which is equal to the identity in the algebra, then notice that the map M alpha, right, is equal to, what is it? It's equal to
Everything times the identity, which would be 1.
I've lost my definition. I'm actually deriving it. Alpha, right? But says that I can write that column by column. I think that's what you're getting at here. This is like L alpha of V1, right?
Mm-hmm.
With respect to the beta basis. And then L alpha of V2, the coordinate vector of that with respect to the beta basis, and so forth, right? But since V1 is the identity, L alpha of 1 is just alpha times 1, right? Which is just alpha. So like the first column becomes the beta coordinate vector of alpha. It's not just alpha itself, like we did last time, because A isn't necessary. I'm not saying A is equal to Rn.
You're saying it's any arbitrary.
Yeah, A could be a set of matrices or even a set of maps. But the point is, if the first basis element is the identity, it is the case that the first column is the coordinate vector of alpha. And then these ones have a similar relation, right? Alpha V2 is really just, how's L alpha V2 go? L alpha V2 is alpha times V2, right? So, this is a formula for that would be this, right? Alpha times V2, the beta coordinate of that. Alpha times Vn. And so the difference between what I'm writing right now versus what I wrote last time we met is just that we didn't have the beta coordinate maps there because we could just, they were just the vectors because we were working with A equals to Rn. So, like the vector is its own coordinate vector in that context. Anyway, there's that. All right, let's see here. So they're isomorphic, meaning that they're isomorphic as vector spaces, and they also the product transforms from one to the other. Specifically here, just to emphasize, you have like m of alpha times beta is equal to m of alpha times m of beta. So here we have a product in A, right, in the algebra, and over here we have a product of n by n matrices. Now we can say more. We can say more. Oopsie. Okay. Paper towels need to dry it out here. So what I'm trying to explain to you at the moment is specifically how we can steal results about matrices over to the algebra. And so I'd like to say some things with authority that are general truths about algebras. For example, if you're in an algebra, in the sense that we've defined, a real associative algebra of dimension n, all right, so it's a finite algebra in the sense of finite vector space dimension. In that context, you give me an element of the algebra, all right, you got three choices. You got three choices. Either the algebra element is an invertible element, it has multiplicative inverse.
Yeah, that's what I was thinking. I was like, the only way you could steal a product is if you could put it back.
Right, yeah. Well, so matrices, they're either invertible or they're not invertible.
Yeah.
Right? And if they're not invertible, they're either 0
or undefined, right?
Or they're something that doesn't have rank n.
Yeah.
They're like less than rank n. They correspond to a map which is not 1 to 1, it's not onto. So this isomorphism that I was just describing to you, it gives us.
Isn't that one of the properties of an isomorphism? That's invertible also. I think that's something else.
Well, isomorphism, so like definition for us, if we have A with star, right? And let's say B with triangle as product, then I'm going to throw this marker out. But I can't throw it out because I don't have an unlimited supply of other ones. So I may come to the point where I have to use that one. Then I need another letter. Let's say
C.
C.
Make it a complex C.
Complex C. Complex C. Oh my! No! No! I do not use C as anything except for complex numbers. That is an evil suggestion, but actually hilarious. But that reminds me. Ever tell you I had a student in like 2016? No, 2017. I forget. A few years ago. His name was Joe. Joe always wanted to make pi a variable. I'd ask him like, "What's a?" No, it wasn't pi. It was worse than pi. There's
E?
7. I'd ask for a new variable name. He'd be like 7. I'd be like, "Shut up, Joe!" Like no less than 10 times that semester. I'm like, "Dang it!" It's annoying. So I'll just use G for lack of imagination. G from A to B is isomorphism of real associative algebras provided G is an element of the linear transformations from A to B. I keep spreading beta on that script DB. You know, this marker gives me such false hope. Like, I start using this marker, it is fantastic, and then about like 3 seconds later, it does this. Anyway, chalk and chalk.
That's what I was gonna say.
Yeah.
I've been looking for a chalkboard online.
Yeah, my wife too. She's like, "I want a chalkboard." I'm like, "I know, but last time I looked, they're like $1,000 for this size." So.
They are overly expensive.
Yeah, I have tried painting with that chalkboard paint, and it's not good. I've even tried putting the chalkboard paint over this material because it's harder than like the wallboard is not hard enough for one thing. It's got too much spongy. It's too spongy. Like it can't take chalk. Even the beautiful famous Haberama chalk.
Didn't they used to write chalk on the windows?
There is that like grease pencils or whatever. Huh. Yeah, you could get like plexiglass and write on that stuff.
Yeah.
Yeah. But then I think you have to, right, like you always see this in like the old battle scenes of World War, or like maybe Vietnam movies or whatever, when they, Navy ship and they're writing on the glass, or
Yeah.
some, I think maybe Hunt for Red October, or I've seen a submarine movie where they're writing on the glass, but.
Yeah. Last time I saw it was the Einstein
I had
series.
I had a
Genius.
dean or a sub-dean or anyway some administrator person where I used to work, and they were always wanting us to like get like glass in front of us and like write on the glass and then like they'll flip it so that it'll be, and like that was like the highest form of like pedagogy, and I'm just like, no one wants to see you looking at them while you're writing. Like it does not matter. This is not like part of math. It's like, how does the professor looking when he writes that equation? That's not part of the discussion. And it's just awkward.
They just wanted to look through the glass and look at you.
Because if you look at YouTube, you'll find these videos where people are like,
Yeah.
and like, oh look, I spent 50 hours making this 10-minute math video. How awesome am I? It doesn't matter. Like, this is so much better. This is natural. Like, this is classroom.
Yeah.
I don't know. Whatever. So this has to be a linear map from A to B, and is isomorphism, is invertible.
Yeah, I thought that was one of the definitions.
It has to be invertible.
Yeah, so if it's not 1-to-1 onto, it can't be invertible, right?
Yeah, invertible implies 1-to-1 and onto. That's right, and it has to preserve the product. That's the new thing. So up to this point, we would just have linear isomorphism of real vector spaces.
Mm-hmm.
But what makes this more than that is that g of x times y is equal to g of x triangle g of y. Where this is like, or fine, let me be more obnoxious. This is multiplication in A. Here, this is the multiplication in B. So multiplication in A gets converted to multiplication in B. This is an isomorphism. It preserves the product in the natural sense.
Okay. But yeah, so like if you get a matrix that has a like less than rank n, it's not going to be 1 to 1 to R2, so it wouldn't even be a good map, right?
Not for what we're doing, but yeah.
Markovich has this thing, he's like bad map, don't use bad maps.
Don't use bad maps.
Yeah.
See, in some sense, it's just a question of nomenclature. I mean, if I say that the m, I mean, it wouldn't be bad. It wouldn't be hard to make m. It wouldn't be hard to make m bad.
Yeah.
Here's how to make m bad. M is a mapping from A to Rn by n. Oh no! See, now all of a sudden, same formula. It's no longer onto because this, it's actually onto this guy, right? And MA of beta is a subspace of Rn by n. In fact, this is an n-dimensional subspace, right?
Yeah.
So there are n squared minus n dimensions left that you're not covering with that map. So like, is M a bad map? I mean, I don't know. Maybe it's just, you're like, well, I can make it not bad by just replacing the codomain here with that.
Yeah,
My question to
you
you-
could do that.
So my question to you is, are those really different? I mean, they aren't technically different, but I don't know. I'm not saying anything useful or profound here. I'll just tell you that, okay?
Yeah, I would just change the codomain.
Yeah. So theorem. Un momento. Sadly, I think I left my big pack of markers in my office. Because I bought a big pack of markers because I thought I was going to be writing in 126, and then things changed and I ended up not being there, which was good. Okay, so theorem. Oh no. Sad.
Markers come dead. Just bashing on the table a little bit.
2005. How old these are?
I did not know markers died.
Oh yeah, they eventually. Well, we'll see what happens. No. Yeah. See the. Oh, interesting. So the black one's cap was ever so slightly not clipped on. That's interesting. So if if G from A to B is as above, then one, instead of using G, I'm going to use phi, all right?
Okay.
Then phi of the identity in A is equal to the identity in B. So it maps the identity to the identity. It maps inverses to inverses for x, an element of A upper, I call it A upper X in these notes. So this is the set of invertible elements in A. Have phi of x inverse equal to phi of x inverse. I may have written it the other way in the notes. 3 inverse maps to inverse, and if x and y are elements of A such that x times y equals to 0, then phi of x times phi of y is equal to 0. Moreover, the image of the zero divisors in A is the zero divisors in B.
So when we're talking about zero divisors, do you mean like things that divide zero, or things that are all divisible by everything?
There are things that give you a way to factor 0 into non-zero factors. Like in a field, the only way to get 0 is
Multiply by 0.
is if 0 is a factor of that product, right?
Oh,
Like
okay,
either
yeah.
0 times, it's either 0 times 0
Oh,
or
okay,
0
yeah, I
times.
got you now. Okay.
But for a zero divisor, the non-trivial zero divisors are what I'm most interested in. The ones that are non-zero and yet give a product of non-zero things, which is 0. This is quite foreign to our usual thinking, right?
No, but I got it once I put it in the sense of like, you know, certain things happen in other algebras that aren't the real numbers, like I squared.
Right.
And
Oh yeah.
If you take an algebra where like your term squared equals 0, it'd be a zero divisor if it's not equal to 0. Oh, and I was thinking would also be interesting if you could find an algebra that would factor prime numbers. That you can map to factor prime numbers.
There are things to say about that. There are algebraic structures which give insight into particular factorizations of primes.
No, I was just thinking, I was like, man, that's something that's like a hot topic right now is prime numbers. Well, prime numbers.
Yep, prime numbers are indeed. There's these creatures called number theorists who care deeply about them. That was it, Matthew. Let's see here. So, the proof of these assertions. There's various ways to prove them. Actually.
Well, I mean, the first one I feel like is trivial, right? Because
Actually, am I forgetting my definition of isomorphism? Just a second here. I feel like that might have been part of my definition of isomorphism.
do you define it in the paper, or are you talking about last lecture?
I believe in the paper I defined isomorphism.
I got psi is A to B, isomorphism to the R vector space is linear, map with linear inverse, psi x star y is equal to psi x star psi y. That's, and then, that's as far as we went. That's the one from last lecture, yeah. But, yeah, the first one, well, I guess that's not trivial.
Well, we can look at my proof on page 11. So I'm like, to prove one, I say simply note for each y and b there exists x such that y is equal to phi of x. And so I give an argument that for each y is phi of 1 times a.
Okay.
something like let y be an element of B,
Mm-hmm.
then there exists x in A.
That gives you
Such
y.
Yeah, phi of x equals to y, and phi of x equals to phi of x, phi of 1
Mm-hmm. Of
A times x, which is equal to phi of 1 times
X.
phi of x, which is
y. Yeah. And so for it to equal y, that would have to equal 1 in the.
and so this is but this was equal to y.
Yeah. So that means for it to continue equaling y, it would also have to map to the identity and
Right.
and be.
So we have y is equal to phi of 1 times y, which is equal to, you can do the same calculation on the other side.
Yeah.
Y times phi of 1. And since that holds for all y, since that holds for all y, that implies that phi of 1a. Now, I am assuming what there, this proof, rests on the assumption that the identity in the algebra is unique.
Oh. I forgot that that's not like a given.
But the proof that the identity is unique is the one you saw in group theory.
Yeah.
See, because AX,
Well, I mean, that's the definition of a group. It's not really a group theory.
AX you could call the group of units in A,
Mm-hmm.
because it is a group with respect to the multiplication, because you've got the identity element, every element in there has an inverse, and it's associative because we're working with an associative algebra. So, like, you know that the identity in a group is unique, so indeed the identity in an algebra is also unique because there is a group sitting inside the algebra. It's got more than that, right? But there is a group there. So we can kind of steal some results from group theory if we're willing.
Well, isn't that the definition of a group? That it has to have a unique inverse?
Oh no, that's a theorem.
Okay.
The definition of group is that there exists an identity, that there's a binary operation which is closed under inverses and is associative. That's pretty much it. If it's commutative, then, you know, E times B is B times A for all.
Yeah.
And then, so that's the proof of 1. The proof of 2 and 3
Are immediate from the definition of inverse and zero divisor, since phi of x star y is equal to phi x star phi y.
Mm-hmm.
2, if you have inverse, yeah, that makes sense.
Right.
And then x, y, such that.
So like,
Oh,
yeah, I mean, oh, I'm okay.
yeah, you're good.
To
Yeah, because if you had well, for 2, I would say like phi of x is all. If you have a y such that phi of x equal to y, that y inverse, and then if you did phi of y inverse, you could break that up.
yeah, I was thinking like phi of x inverse
Mhm.
is phi of x